Let's try an example using the Clausius-Clapeyron equation where we take a look at ethanol, and the normal boiling point for ethanol is 78.3 degrees Celsius, and its heat of vaporization from tabulated data is 39.3 kilojoules per mole. What would be the vapor pressure in torr at 50 degrees Celsius? So if you remember, the Clausius-Clapeyron equation is this relationship between vapor pressures at different temperatures, and it's the natural log of P at some temperature 2 divided by the vapor pressure at another temperature, we'll call that temperature 1, is equal to the change in enthalpy of vaporization divided by the gas constant times 1 over that first temperature minus 1 over that second temperature. Okay, so that's the equation. And what we're given here is the normal boiling point, which is 78 degrees Celsius. So we'll let that be our temperature 1. And the normal boiling point means that the pressure there is equal to 760, because normal is at normal atmospheric pressure. So we'll call that 760 torr. And the heat of vaporization, of course, is given right here, 39.3. Our T2 is going to be the 50 degrees Celsius, and we're looking for the P2. Now, in the Clausius-Clapeyron equation, because we're using the gas constant, and the units for the gas constants are joule per mole Kelvin, our temperature units need to be expressed in units of Kelvin. So T1, then if we add 273 to T1, which was a 78.3, then that value is 351.5 Kelvin for the T1, and T2 would be 323.2 Kelvin. So those are our temperatures that we're going to plug in right there and right there. Our R value, of course, is the gas constant, 8.314, and that's in units of joules per mole Kelvin. The delta H of vaporization, of course, is always given in units of kilojoules, but we need our units to match. So this we're going to express in units of joules. So I'm just going to write it up here real tiny. That's going to be 3.93 times 10 to the 4th joules per mole. It's the molar heat of fusion. And then we were told that P1 was, we're going to let that be the normal. So that's going to be 760 torr. Okay, so now we've got all these different numbers. We just need to do the math and solve for the solve for P2. So let's see here. Let's put these numbers in, and we'll say the natural log of P2 divided by 760. I'm going to leave the units off for now for clarity, since we sorted out all of our units previously. 3.93 times 10 to the 4th divided by 8.314. times 1 over 351.5 minus 1 over 323.2. And you can do all the math here, and the natural log of P2 over 760 is going to equal negative 1.18. Okay, so we need to clear this natural log by raising this to the power of e. So raise this to the power of e and this to the power of e, and that just gives us P2 over 760 is equal to e to the negative 1.18. You're going to have to plug that into your calculator, and that's going to equal 0.307. So solving for P2 is just going to be 760 times 0.307. Remember, the torr unit was still attached to that 760, and that's going to equal 233 torr. So as predicted, at the lower temperature, the vapor pressure is lower.